Prefixes, conversions, and scientific notation. Here are your priming questions. Before we get to prefixes, I want to quickly talk about accuracy and precision. If you look at this diagram, you can see accuracy is across the top and precision is down on the column on the left. And so if you're both precise and accurate, this is what it could look like. This is just an example. Think of this as a dartboard and darts that you're throwing. In order to measure precision, you need to have a large sample size, which means you have multiple trials or you have multiple data points. So in this case, you would have multiple darts. And so if you have multiple darts and they're all at the bullseye, you're both precise and accurate. Accuracy refers to how close you are to your intended target or to what your goal is. In this case, the bullseye. If you are precise but not accurate or inaccurate, you would look like this. So your darts are all located in one general area, but it's not where you desire it to be or where it should be. This means that you have some systematic error somewhere. It means you're doing something wrong, but you're doing something wrong consistently. If you are accurate but not precise or imprecise, you can see that these would average out to make it look like it's accurate, but when you look at the data points or you look at what we call the standard deviation, you would see that these data points are very spread out. And if you're both inaccurate and imprecise, then the darts would be spread out and not even close to where you're trying to get to. And so whenever we're doing our labs, we always want to be as precise and accurate as possible. Your graphs and your calculations will tell you whether you are accurate or precise or one or the other or neither in some cases. So keep that in mind. Your prefixes. Here is a list of the standard prefixes for the metric system. You need to memorize the ones from 10 to the 12th to 10 to the negative 12th. So that would be tera to pico, except for hecto, deca, and deci. These are still prefixes, just not ones that are commonly used or ones that I will commonly use in this particular classroom. And so you want to make sure that you're familiar with all of these. And you can memorize the multiplier if you want, but I would say that the power of 10 is going to be much more powerful for you and much easier to remember because you just have to take note of which power of 3 it's going to be in most cases, except for centi. So keep that in mind for all of these. So, scientific notation. All of you have seen scientific notation before, so this should be a very quick review. Let's say we want to write 652 kilometers. In scientific notation, you would write 6.52 times 10 to the, and you would look at how many decimal places you've moved, 10 to the second kilometers. Now, some of you may or may not be familiar with the E notation though. In my particular class, I use E notation, so that means that I will accept E notation on quizzes, on tests, on homework, and things like that. Our online practice will also accept E notation. Now, where the E notation is on your calculator is going to be over here. So if you look at your comma button on your calculator, second comma will give you that E. And all that does is it replaces the times 10 part. So the way you could type this into your calculator, and it would be the exact same value, would be 6.52 E2. And if we're writing this out, we would always want to add our units, so this would be 6.52 E2 kilometers. These two values are exactly the same. You also want to make sure you keep in mind the number of significant digits. 652 kilometers has 3 significant digits, so that means even when we convert it to scientific notation, we need to make sure we have 3 significant digits. If we look at 3,200 liters, scientific notation would just be 3.2 times 10 to the third liters. Take note that these two zeros are not significant. If we want to write this out in E notation, the way I would write this would be 3.2 E3 liters. And that's it. So this original value has 2 significant digits, so do each of these. I want you to give these 2 practices a try, and we'll check those in class. Now, dimensional analysis. This is going to be for our conversions. This is also called the factor label method. if you are familiar with that. So it roughly looks like this. You have your starting value in units on the left, you draw a long horizontal line, and then you'll have these vertical lines, and at the very end of this in the upper right corner, you'll have your final units. That is your goal. And what you put in these places are the conversion factors that do not change the true value, they just change the units. And so what you want to do is you want to think of this as a big fraction, and you want to cancel out units on the top and bottom until you are left with the final set of units that you want to end with. So I'll give you some examples of this. So let's say we want to convert 18 years into seconds. Most of you probably know some shortcuts to be able to do this, but I want to show you how to do this with dimensional analysis. So we start out with what we are given, so 18 years. We draw a horizontal line, and we want to end with seconds. So we need to be able to convert or cancel out our years and ultimately get to a unit of seconds that are left. And so if we need to cancel out our years, that means we need to put our years on bottom, and it's going to be easiest to convert years to days. And a quick question would be, why not months? So we can talk about that in class. So 1 year, we'll go and say is roughly equivalent to 365 days. It's not exactly, but this will be good enough for this. From here, we can cancel out our years. We're left with days, which obviously are not seconds. So we need to cancel out our days by putting the days on bottom here, so they'll be able to cancel out. And I don't memorize how many seconds are in each day, but I know how many hours are in each day, so we can convert days to hours. So we know 1 day is equal to 24 hours. Now, some of you may know directly how to go from hours to seconds. If you do know that, then you can go and convert that directly there. But if you don't, we can put hours on bottom here, and we can say we know hours to minutes. So 1 hour is equal to 60 minutes. And now we can do our final conversion. We know that we need to cancel out our minutes to seconds. So 1 minute is equal to 60 seconds. So when you look at this, each of these conversion factors, let me actually use a different color. So each of these conversion factors, what you'll notice are equal to 1. 1 year is equal to 365 days. 1 day is equal to 24 hours. And 1 hour is equal to 60 minutes. So we are not changing the value of our initial value. We're multiplying it by values of 1 in order to convert the units to get to what we want. And so when you work this out, you multiply across on top, you multiply across on bottom, and then divide the top by the bottom. In this case, the bottom has all 1s, so all we need to do is multiply across on top, and we get 18 times 365 times 24 times 60 times 60. And I get 567,648,000. And if we look at this, we initially have 2 significant figures. And so I would round this to 5.7 times 10, or E. And let me count this out. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. This would be seconds. Now, using our prefixes, 7.23 millimeters into kilometers, we again start out with what we're given, millimeters. We draw this out. We want to get to kilometers. So millimeters, if you know the number of millimeters in a kilometer, you can go and convert directly. But if you don't, it's always safest to convert to the base unit first. Millimeters and kilometers, our base unit is the meter, so we want to convert our millimeters to meters first. So we need to cancel out our millimeters, so we put these on bottom, and we want to convert to meters on top. Now, the way I do this, I always use the biggest unit first, and so I say between meters and millimeters, meters are biggest, so I put a 1 with the biggest unit, and then I think, how many millimeters fit into 1 meter? And we know there are 1,000, or I use the powers of 10, so we know that there are 10 to the 3rd. You can do this the other way using the negative exponents, but for me personally, I like to use positive exponents, and we can talk more about this in class. So now I can cancel out my millimeters. I'm left with meters, but I want to get to kilometers, so I need to cancel out my meters, put them on bottom, put my kilometers on top. Now, kilometers are bigger than meters, so I have 1 kilometer, and that's equal to 1,000 meters, so I have another 10 to the third on bottom. I can cancel out my meters, and so now the units that I'm left with are kilometers, and that's where I want to be. And so, I can, let me go and erase this now, so I give myself some space. I can work this out, and you actually don't even need to use your calculator at this point, because if you know your rules for exponents, we can see that this is going to be 7.23 times 10 to the negative 6 kilometers. And that would be our answer there. Try these two problems on your own. We'll come back to that in class and check your answers. What I want to try to do is show you how dimensional analysis can be more powerful, and this will come in handy later on in the term as well. So before we were working with just one set of units. Now I want to show you how you can work with two set of units. So in this case we have grams per milliliter. We want to get to kilograms per microliter. You'll notice that these are densities, a mass per volume. And so we started out the exact same way. We have 5.3 grams, but now it's a little bit different. Rather than doing grams per milliliter on top, we put grams over milliliters like this. Remember, we can think of this as a fraction. Now, where you have to be careful is, at this point, we have to choose a set of units that we want to convert. We can't convert both at the same time, so you choose one. I usually choose the top one to do first. It really doesn't matter which one you choose, though. So I want to convert my grams to kilograms first. So I put grams on bottom to cancel that out, and kilograms on top. Now, kilograms are bigger than grams. I put 1 kilogram is equal to 1,000 grams. So now I can cancel out my grams. I'm left with kilograms on top, and that's what I want. So I'm done with my mass. Now I want to convert my milliliters to microliters. And if you know the conversion directly, you can do that in a single conversion factor. But if not, we'll go directly to liters first and then to microliters. So we need to cancel out our milliliters. So in this case, milliliters are started out on bottom. We need to put them on top to convert. So milliliters on top. And then our base unit for volume is the liter. 1 liter is bigger than 1 milliliter. So 1 liter is equal to 10 to the third milliliters. So we can cancel out our milliliters. We're left with liters. We want to convert to microliters, and those should be on bottom. And if we look at this, when you convert our liters, or cancel them out, so liters on bottom, so we need to put them on top. And we can put microliters on bottom. Liters are bigger than microliters. So 1 liter on top is equal to 10 to the 6th microliters. That's in our powers of 10. Cancel out our liters, and now we're left with this. And if you know your rules, we can see that these will cancel out, and that will give us 10 to the 6th on bottom. And if you know the rules for that, that means that it's going to be 5.3 times 10 to the negative 6, and our units are going to be kilograms per microliter. Give that a try for these 3 as well. We'll check those in class. And here are your priming questions again.